The sum of an infinite geometric series. Compute each sum below. Give exact values, not decimal approximations. Notice there are three series here. And a series is what? Is actually a sequence where you add those sequence terms an infinite number of times. So here is the concept of infinity. Those three dots here says that we will add things forever and forever and forever and forever. This is sort of strange. Why would we add things forever, forever, and forever, and forever? Well, sometimes we run into those situations where we need to make predictions off of reiterations. Same thing here. Here's the concept of infinity. You're going to add these terms over and over and over again. And there's only two things that could happen. You either have a sum that is finite, and finite in this case means tangible, reachable, concrete. It is a real number, and that's what we mean by finite. Or you get something that's not finite. In other words, you would say the sum will not exist. It's not reachable. You can add things forever and forever and forever, and you won't get to something that is tangible. Now, I'm going to do this a little bit differently. I'm going to give you what I call a calculus technique on how to find the sum of a geometric series. I'm actually going to take a very, very simple series. I'm going to take this geometric series where you just have a common ratio raised to the k power, but we're going to start k at 0 and then run this to the concept of infinity. Notice this really just says r to the 0 plus r to the first power plus r squared plus dot dot dot. And of course, if you simplify that, the first term is always going to be 1, and then plus r squared plus 3 dots. Now this actually converges to a 1 over 1 minus r if the absolute value of r is less than 1. Now I'm going to write this much cleaner, and typically in mathematics we could write things in an if-then statement. So if the absolute value of r is less than 1, big comma, big comma, big comma is right there. Then we make this conclusion. Then the geometric series r to the k, starting at k equals 0 to infinity, is simply going to be 1 over 1 minus r. And that is a beautiful sum and rather simple formula. We're going to use this formula to figure out the sums in A, B, C, and D. Let's start with A. Example A. So I'm just going to start off by copying the problem again. And I can see that there is a common factor. And that common factor is 2 times negative 5. And let's see what's left. What is left? Well, we have a 1 plus a what here? A negative 5, right? If you multiply, if you distribute, you're going to see that you have 1 plus negative 5 plus another what? A negative 5 squared. So we're just simply taking your factoring skills and seeing that there is a nice geometric series here. So this is now equal to what? This is now equal to negative 10 times this geometric series, which is negative 5, negative 5 is the common ratio, And I'm going to use k. There it is. And I'm going to put a period there. Since the absolute value of negative 5 is actually equal to 5, which is greater than 1, we could make this conclusion. The sum does not exist. And we're done. So in this case, we couldn't find the sum, but you did have to show the work and evidence to see that the sum doesn't exist. So I'm going to circle this. And then this is your final answer. Final answer is pretty meaningless unless you show your work. So that's why I just circle the whole thing. I'm going to need more space for example B. So I'm going to go ahead and erase the board. If you need to, remember to pause the video. Example B is very, very similar. Can you see a greatest common factor from all those infinite terms? I'm going to first recopy the problem. So 4 plus 4 times negative 3/7 plus 4 times negative 3/7 squared plus 3 dots. Don't forget those 3 dots. That means you're running this to the concept of infinity. We're going to add this an infinite amount of times. There is a greatest common factor, and that is 4. Every term has a 4. Let's factor out a 4, and let's see what we have left. We have a 1 plus a negative 3/7 plus a negative 3/7 squared, and we indeed have a geometric series here. This is now equal to 4 times the summation k equals 0 to infinity of the common ratio of negative 3/7 raised to the kth power. We do know that this converges. So why don't we just keep writing? We're going to say 4 times 1 over 1 minus negative 3/7. We could certainly simplify this. I'm going to multiply by 7 over 7. Let's see what we get. We get 4 times 7 in the numerator, all over 7 plus 3. Gorgeous. And 7 plus 3 is just 10. We could reduce factors. So 2 over 5 times 7. So 14 over 5. And who would have thought adding all those infinite numbers will simply get you 14 over 5. So there's the final expression for part B. Notice in part B you're not solving for anything. You're simply manipulating this expression right here. You started with this expression and you ended with this final expression. I'm going to go ahead and circle all the work as well. Moving on to part C. Part C says there's a series here where the sequence terms are 5 times the common ratio of 1/2 raised to the kth power. But we start with the index of k equals 1, and we run this to the concept of infinity. Let's copy the problem again. And what do all these terms have in common? Well, all these terms have a 5 in common. So let's factor out a 5. And I don't really want to start with k equals 1 here. I would love to start where? I would love to start with k equals 0. If we're going to get this to k equals 0, we know it converges to that. 1 over 1 minus r. So, how can we get this to start at k equals 0? So we're going to re-index everything here. I'm going to show this off to the side here. We're going to replace k with k minus 1. Yeah, that's going to do it. So if you replace k with k minus 1, what happens to this equation here? So you replace k with k minus 1, then you get k minus 1 is now equal to 1. Oh. Excuse me. Don't replace k with k minus 1. I meant to say replace k with k plus 1. Then this equation over here, if you replace k with k plus 1, then we get k plus 1 here is equal to 1. So let's put a k plus 1 there is equal to 1. And if you solve for k, we now start at k equals 0. All right, we got it. 5 summation. Now we have k equals 0. Run that to infinity. Then we have 1/2, and we replace k with k plus 1, so this is k plus 1. These are in fact the same geometric series, starting with a different index. Now, what do all these terms have in common? These all have a 1/2 in common. You could easily see that by mastering your rules of exponents. And now you can see there's a common term of 1/2. I'm going to take this 1/2 right here. Every single term actually has this 1/2. So let's factor that out. We have equals 5 over 2 times the series and that is gorgeous because we could actually find its sum. This is multiplied now to 1 over 1 minus 1/2, which is just 1/2, by the way. This is going to be 5. Who would have thought the final expression would be 5 after adding all those numbers together? Let's go ahead and circle the final answer. But once again, show your work. Without your work, your answer is pretty much meaningless. Moving on to example D. Oh, did I say example D? Yes, I did say example D. This one got mislabeled. We actually did C. So why don't you get a head start on example D, while I just erase the board here. Example D, the series starting with j equals 1 to infinity times 3 with the common ratio of negative 4/7 raised to the jth power. Now, what do all these terms have in common? All these terms have in common is a 3 times negative 4/7. Yeah. And what's the first term now? I might be going too fast. So why don't I show you what I'm doing here? Let's write out the first few terms. This is 3 times negative 4/7 plus 3 times negative 4/7 squared plus 3 times negative 4/7 to the third power. And this never stops. I'm going to write the next expression, which is the greatest common factor, 3 times negative 4/7, and let's see what's left. What's left is a 1 plus a negative 4/7 plus a negative 4/7 squared, and so on and so forth. This is a nice and easier approach. Now we have what? Negative 12/7 as the greatest common factor. Multiply it by the series. I'm going to use k equals 0 to infinity. The common ratio is negative 4/7 raised to the k. We know this sum is going to exist because the absolute value of 4/7 is 4/7, which is less than 1. So knowing that, we could just keep writing to find the sum. And I'm sure you could take it from here. I'm going to multiply top and bottom here by 7. Another fancy name for 1. And let's see here. You get negative 12/7 times it by 7 here over what? 7 plus 4, which is 11. Yeah. This is a really nice number. This is just negative 12 over 11. That is the final expression. Make sure you show your work. Be neat, be orderly, and be amazed. You add up a bunch of numbers. Well, not a bunch of numbers, but an infinite number of numbers. And it could actually sum up to something very finite or concrete or tangible. Not always the case, but this is still truly amazing.